Welcome to the last assembler lecture, in which we're going to be covering what I will call high performance assembler in line with the chapter in the textbook. But a lot of what we're going to discuss today actually is not just applicable to assembler, though obviously in an assembler context it's more important than in a traditional compiled language sense. A lot of the lessons we learn here can actually be applied much further than just assembler. So I just want you to keep that in mind as we go through some of these kind of tricks to getting more out of your assembler code, because a lot of those tricks actually apply to regular code and regular data structure use in other languages. So we're going to discuss a couple of common and effective ways to optimize your ASM, or as I said earlier, code in general, but again, it's more relevant to the assembler context. Now, it should be noted that it's not always actually the best approach to try and optimize all of your production code. Now, by that I don't mean that you should intentionally have inefficient code, but when it comes to the kind of optimizations we're going to discuss now, for example, the ones that aren't really changing the big O notation of the algorithm that you're implementing, you should really only invest that time if you can actually predetermine where the bottleneck in your system in fact is. Now, generally speaking, it's hard to speculate where the true bottleneck is. Sometimes you can, but not always. So what generally happens is you will implement a more production system, and then you will do some kind of stress testing on the system. During the stress testing phase, you'll actually be able to identify, using proper performance profiling tools, where the kind of bottleneck sections of your code are, or even not necessarily the bottleneck, or just places where your code is executing a large percentage of its time. So say you had a very large enterprise system and you had one function that was being called 20% of the time, that function being all that was executed for a whole 1/5 of the time that the program was running. That's probably a good sign to you that there might be some fruit to find by optimizing that function's code further. So that's something I want you to kind of take away, is not to pre-optimize unnecessarily, rather determine that it's worth doing that optimization and then going from there. Again, I don't want that to be misconstrued to say that, oh, you can just have inefficient code. By this I mean that a lot of these optimizations might be considered to be kind of minimal type of optimizations, but if your code is executing so much of its time with the small section that we're going to try and optimize, it's definitely worth the small gains by performing these kind of micro level optimizations. Now, obviously in the essay context, we have additional constraints that we would like our programs to finish executing before the power actually cuts. But in many situations, we do have some kind of computational budget, and obviously the less time our algorithms or our systems take to run to achieve a certain thing, the better it is for us on multiple levels. Now, something I should kind of make clear is that an optimizing compiler, so let's say you're optimizing your C++ code and you have even O1, so the first level of optimization, C++, you'll actually find the compiler does a lot of the tricks that we're going to actually do. But it's actually quite important to understand why the compiler is doing some of these optimizations. Now, generally speaking, a compiler will actually perform these tricks that we'll go through tirelessly, and it will never miss a beat. And unlike us, where we might forget to optimize a specific function, it will kind of apply this technique across the entire program, and generally speaking in quite an intelligent fashion. And actually, compiler technology has actually advanced quite a lot in the recent years, particularly C++ compilers, because of the growing interest in the language again. For a long time, we were kind of at the level of C++ 98, and there was your general GCC, but a lot of the high performance compilers were actually almost somewhat proprietary, owned by Intel and the likes. But the current generation of C++ compilers are very optimized. Now, generally speaking, this means that if you are planning on using one of these kind of optimization techniques for your code, these kind of micro level optimizations, in a compiled context, let's say you have C++, it's likely that we're going to have to use a non-obvious technique to actually get better performance than the compiler. So that's one thing to keep in mind. But what I think is a very useful lesson actually is to learn from the compiler. Now, it's quite easy to actually get the assembler listings for your actual C++ program. and you can see the tricks that the compiler has performed. So try and disassemble the code, for example, at normal compilation level or optimization level 1 or 2. For the moment, just look at the speed variance if you're interested. Obviously, there is space-time optimizations. Space optimizations, not space-time. And I'm not going to ask you what a disassembled C++ code would look like, for example, in the test, but I think it is very informative to actually look at that translation. Now, one thing you will notice if you disassemble C++ or C code is that there is still quite a bit of boilerplate code. And that's because though the compiler is applying these techniques that we're going to discuss kind of ruthlessly throughout your whole program, to ensure it's sufficiently general the way in which it applies the techniques, it sometimes adds a little bit of unnecessary bloat in the process. So if you were doing some things yourself, you could eke out a bit of performance by losing on the generality. And that's generally the way the trade-off goes, that you can eke out sometimes more performance at the cost of generality. But again, if you're optimizing for a very specific use case, you're generally happy to make that kind of sacrifice. One of the first things we're going to go through is, in some sense, a very fundamental type of optimization. And again, not just specific to assembler context, but it is one that I feel is often overlooked or not properly considered. And this is efficient use of the cache. Now, luckily in this course, we have both sides. We have the theoretical side of what different caching schemes there are from chapter 6 and how we can manage memory. But on this side, it's kind of important to make sure that our programs are written in a way such that we can best exploit the concept of caching. Now, obviously our aim for any type of program is to keep the processor as busy as possible performing productive instructions. Whereas if our CPU is working hard and then suddenly it needs to access a bit of data and it's not available in the cache, the CPU now has to sit around and wait while that data is fetched from a different level of memory. It might be, say, if say for example you have a miss at level 1 cache, it might look at level 2, then level 3, or it might have to go all the way to main memory, or even worse than that. So as soon as you get one level of miss, you actually start having your CPU waste time. The worst case scenario obviously is if the data you're accessing is not in any level of cache, it ends up inducing a great degree of latency, so a lot of wasted time. So our aim is to obviously maximize the cache utilization instead of non-cache based memory. And how do we go about doing it? Well, the concept is actually quite simple, though as I mentioned, it's often ignored. And the idea is to simply organize our algorithm to exploit data locality. Okay? By that I mean that I should rather access data elements that are near the current element I'm looking at, instead of jumping around the whole time. Now, I'll give you an example that isn't actually in the textbook, I don't believe, but I feel it illustrates the point quite nicely. Let's say we had a linked list. So just a simple abstract example of a linked list. And each of these nodes were at some point in time allocated in memory. So as we were doing computation, we performed another malloc and we inserted the node. And then I, for example, say I want to iterate through this linked list. I'm looking for a specific value. Maybe I'm looking for the node that contains the value 7. And I start at the front of the list and I'm now going to iterate through my list looking for this value. So in principle, I would start at a specific address. I'd follow the next node and I'd end up at the next, I'd follow the next pointer rather, and I'd end up at the next node. And I can repeat this process. But the question you need to ask yourself is, what location in memory is this node compared to the location in memory where this node is? And the same thing applies for the next node. Now, we have no guarantee that this node is stored next to this node in memory. In all likelihood, it will actually be quite scattered, particularly if we were over time allocating new nodes during the computation of our program. What this means is that given that I don't have a guarantee that these nodes are contiguous in memory, when I move from, say, this first node to the second node, the odds that I get a cache miss, so I was unable to find the other node in my cache, is actually much higher, which means actually, even though linked lists are pretty bad in terms of traversal, I mean, it's always order n looking for a specific element, or at least with a standard linked list, unless we do something fancier, it gets worse because not only is it order n, which in and of itself is not ideal, it's also going to be very cache ineffective in that it doesn't exploit data locality. Now, there's actually a relatively simple way of merging these two concepts, and that would be, for example, to allocate a contiguous array that would store many nodes, and instead of just dishing out a new node using a raw malloc, instead you take from your pre-allocated pool. Now, that seems like it might be a little bit wasteful, and it can be to an extent, but if you're traversing a data structure frequently, ensuring that data locality can make the world of difference in terms of how well your algorithm actually performs. So you'll see a lot of the implementations of the STL containers, so the C++ containers like their vector, stack, their list variant, as well as their trees, generally speaking, have a version which tell you if they are cache coherent, and basically that's their way of saying that it's been designed to exploit that data locality, and at no cost really to the user. A little bit of extra space, but we can handle that for the trade-off. So that's just an example of data locality. Now, this might be a little bit a more complicated example in the sense that we're thinking about a data structure as well as data locality, but we can extend this concept to something very simple, just iterating through elements of an array. So let's look at a little bit of an illustrative example. So you see here, this is a situation where we want to perform 10 billion exclusive OR operations on quad words. Okay, so I just want to XOR two values together and store the result in a specific location. So you can think of me having some kind of sum variable and XORing all the elements in an array. Okay, so basically I just want to perform 10 billion exclusive OR operations on an array. Okay, so I just loop through it. Now, let's consider what would happen if the arrays were of different sizes. So here we see at the bottom of this graph, we have the array size in bytes, and we're going to perform 10 billion exclusive ORs every time in this experiment. So even if we have an array of the small size of, just say 10,000, we will loop over and over and over that array until we get to 10 billion computations, so 10 billion exclusive ORs. Now, what this means is that in principle, regardless of how big this array truly is, we're performing the same amount of exclusive ORs. So you may naively assume that it wouldn't be faster or slower because, depending on the size of the array at least, because I'm performing the same amount of calculation. But the reality is actually we can get quite a different performance output. So you'll see on the left hand here on the y-axis, we have the seconds to process 80 gigabytes. So that's basically 10 billion quad words is 80 gigabytes of data. And you'll see that if we have a small array of 10,000, we can actually process that 80 gigabytes in 1.5 seconds. Okay, this graph is a little bit old. It was from the first i7 generation. I think this was on a 9200 processor. So this is, I think, 2007. So it's an old i7 processor, but the principle here stays exactly the same. Now you'll see that as my array size starts increasing, I end up getting worse and worse performance. So much so that when my array is at 10 to the 7, I mean, we're worse than twice as bad. Okay, we were at 1.5 seconds originally, and now we're at 4 seconds. Now, can you imagine if this is an operation that happens thousands and thousands of times? Suddenly things are taking a lot more tangible time than they were before. Now again, I'm not performing more or less calculations. All that's actually happening here, and the reason we're getting the slowdown, is that because the array is larger, the odds that I end up encountering a cache miss, because obviously this whole array is not going to fit in cache at this level, it has a fair shot at that size of fitting into cache, but definitely not at 10 to the 7, it means that I'm more likely going to have my processor sitting around waiting to perform its next XOR operation because it needs data to get to it from memory that wasn't in the cache, or at least not in the cache level of L1 or L2. It had to go all the way to L3. And then obviously the worst case would be going all the way to main memory. And we see that you kind of have this staggered situation, that you can kind of see that this kind of gradient is a little bit different to this gradient, and then this last gradient over here. And this is actually approximately the situation where we could fit most of the stuff in L1, most of the stuff in L2, most of the stuff in L3, and at this point we're actually mostly dealing with being in main memory. At that point we don't get any slower because generally speaking we have more than enough RAM for this size array, because that's not 80 gigabytes, it's considerably smaller. This is maybe, say, I think 1.5 gigs of RAM. We can easily have enough RAM to cater for that, so we don't see a further degradation. But actually what would end up happening is that if this array got even larger than this, we will eventually, though you would have to exhaust all your available RAM, you will actually see even further deterioration in time. But it's kind of hard to achieve that. But it's very interesting to see this kind of behavior actually coming up in practice. Now, this feels like a somewhat artificial example. You can say, okay, fine, we want to perform 10 billion exclusive OR operations, but why would I be doing it on a small array? This feels like an odd example. Now, it is artificial, but it demonstrates this behavior well. Let's actually look at an example, though, or a use case of this notion of cache coherence to kind of get a feel of where we could use this technique quite naturally. And that is with something very fundamental, which is that of matrix multiplication. So for the sake of simplicity, let's assume we want to multiply two square matrices. So basically here I want to multiply matrix A with matrix B, and the output of this would be another matrix. Let's call this C. Okay. Now, it's a simple enough calculation, but the manner in which you do this calculation can actually vastly change how fast it would actually perform. Now, I don't mean that we can maybe get a better order algorithm, which we actually can. There are clever ways of achieving a high complexity or a better notation complexity for even matrix multiplication, surprisingly. But even if we fix that, so we fix the fundamental algorithm we're using, depending on how I move across these elements in my array or my 2D arrays, it will actually change how fast this code will execute in practice, particularly as these matrices get larger. So just as a very quick recap, if you're a little rusty on matrix multiplication, the general idea is that in order to obtain this first element in matrix C, so this one we're going to call C, I end up taking the dot product between this row vector and this column vector. And the dot product is simply a component-wise product of sum of products. So it's simply A11 times B11 plus A12 times B21. And we proceed in this fashion all the way down until the end, where I'm going to be adding A1n to Bni. And what I've just described can be easily illustrated in that summation. If you're a little bit rusty, the easiest way just to make sure you know what's happening here is this is just an extension of using AX, where that's a matrix and that's a vector, and I'm simply multiplying them together to get another vector. But even if you don't remember the simple linear algebra here, in essence, all you need to really understand is that we have these sums, okay? Where in the way in which we would personally calculate it is I would literally iterate from left to right across this one row, and I would iterate from top to bottom down this column to get the first element. And I would repeat the process using the first row and the next column to get this element, and so on and so forth. Okay, so simple enough algorithm, we can implement it. Let's look at a simple implementation in any high-level language. Here we have the algorithm, which is pretty much in line with how I visually showed there that we would perform the multiplications. It's very much in line with exactly how that sum is formed, or sum looks. And it results in having a triple nested loop, okay? And we can actually quite quickly look at this and figure out what the notation would be. This first one goes from 0 to n, next one goes from 0 to n, and the last one goes from 0 to n as well. The reason it's so straightforward as well is because these are square matrices, so they're n by n. So it makes this calculation a little bit more direct, but this tells us that the order of this matrix multiplication is n cubed, where n is the number of elements in a row, for example. Whereas we have n squared elements in total, and it will be n3 to perform matrix multiplication. So here we have our straightforward algorithm. So you'll see this first loop is basically me starting at this row, and then once I'm at that row, I'm going to then pick a column, which would correspond to me picking which column I'm looking at. And then this last loop here is how I would actually iterate down that column. So you would see here that I'm iterating down this column in this term here, because I have bk, j, and I would be iterating at the same time along this row because I am changing the column component over here. So you'll see that the kth component is changing. So simple enough, but something I think I should just make clear is, generally speaking, we assume that even though these matrices are square, that they've been allocated such that the first row is next to the second row and is next to the third row and so on. So we assume that it's been allocated in one long contiguous chunk, and that's generally the way it's done. I mean, you could use a normal two-dimensional allocation, but it's actually worse from a cache perspective. So we're going to even assume that we've made a good decision for matrix multiplication at least, and we actually have one contiguous block of memory, though we've done it in such a way that I can still access the components straightforwardly. Now, you'll see here that we actually have three indices that we can iterate over. We have I, j, and k. Now, fundamentally, nothing restricted us to doing it in this order, except for the fact that it's perhaps the most natural way for us to do it based on the way in which matrix multiplication is defined. But technically, we could rearrange them in any way we want, and we could actually get a working algorithm doing that. We'd have to tweak a little bit of the inner workings to make it function, but we actually could change the order in which we iterate. So we really have the situation where, in this case, I'm iterating over I, j, and then k, but I could actually arrange these three elements in any order. I could iterate over k, then j, then I. So how many different ways could I actually have rewritten this code? How many different ways could I have iterated over those three indices? Well, simple combinatorics from WTW 152 or even high school maths really means that we know that this would simply be 3 choose 2, which is equal to 6 possible ways. Alternatively, you could simply say, well, it's how many ways can I, if I had 3 open slots, how many ways can I place I? Well, I have 3 choices there. So say that was the choice, so that was 3 options. My next term, say I want to place j, how many choices do I have? Oh, I have 2 choices times 2, and k is predestined because there's only one option, so times 1, which would equal 6. So basically, these two things are just equivalent to each other, but in case you were rusty. But now the question is, why do I bring up this idea that we could iterate it in different ways? So there are 6 possible unique ways of iterating. The question is, which is best? Well, in terms of correctness, we could write our code such that no matter which way we arrange I, j, and k, obviously we have to tweak the internal contents a little bit, but in principle, we can always get a correct solution. So what I mean by best is I mean which one would be the fastest. And in this case, the way we'd be able to assess which one is more or less likely to be fast is based on which one is more cache coherent. And by cache coherent, I mean which one would exploit data locality better. So let's look at our kind of straightforward approach that we already described, where I iterate over I, j, k. So this is one of the 6 options. And you'll see what actually happens here is I've illustrated in this picture how I actually do the iteration. So you'll see here that I first select I. Okay, so I've selected this I. Okay, now let's look at how I access the elements of A, B, and C. So C is obviously the result of the product here. So just again, it's just A, B is equal to C. How am I actually accessing these elements? Well, you'll see here that for A, in the inner part of this loop, I'm iterating across k from 0 to n, where the k is being used to move me across columns. So I'm literally moving from this element to this element to this element as k increases. Okay, but now remember I said that all of these arrays are basically lined up next to each other. So this would be row 1, row 2, and so on. But this tells us that when I move, say, from this element to this element, the odds that if this element was in cache, this element will also be in cache are pretty high, which means I'm actually getting a good cache coherent iteration in that I'm moving in a direction where I'm likely to find another element in the cache. Now, obviously, there'll be a point where you've exhausted the cache, but what's also good is that, say, for example, I'm iterating like this, and I got a cache fault here. Okay, so say that that element wasn't in the cache. Now, remember, caching doesn't just load a single element. It normally loads some kind of contiguous chunk, depending on what caching scheme you use and the size of your cache. But it means that if I did have a cache miss, and I loaded the data for this element into my cache, it means the odds that this element now would be in cache because I did this previous load is actually pretty high. So it means that this iteration from left to right is actually very good in terms of avoiding too many cache misses. So it's likely I will get a lot of cache hits. Now, if I look at how I access the elements of B, things change a little bit. So you'll see here that the way in which K is affecting my access is as follows. That in some sense, or in the inner loop here, J becomes fixed because we fixed it over here. And as K changes, I will be moving from this row to this row to this row and so on. But now because this row is not necessarily going to be very close to this row, the odds that I get a cache miss moving from this element over here to the next one becomes a lot higher. Now, in this example, it looks, in this pictorial version at least, it looks like it's unlikely because this matrix is small. But imagine I had a row that had, say, 1 million elements. The odds that this element and this element are in cache at the same time when there are 1 million elements apart becomes very low. So iterating down like this from row 1 to row 2 to row 3 is a high risk of getting a cache miss. Okay, so the odds that I end up spending time waiting for memory to be loaded into my cache or for the CPU to gain access to is very great. So you can think of this first situation as being a low risk, and this next one as being a high risk. Okay, low risk of a cache miss, high risk of a cache miss. And in the last case, with regards to the element of C, well, that's a zero risk situation really, because the element stays fixed when I'm dealing with it. Once I've started accessing it, and I only actually touch it once when I load in the sum, I never have to access it again, so I'm not performing any iterations over it. So even if it was a miss, it would just be a miss in isolation, and I wouldn't have to worry about it again until I stored a new result. So in this sequencing of IJK, we really have a low risk, high risk, and a zero risk entity. So how would this compare to a different way of iterating? Well, let's look at another example. And this is one of the examples that doesn't perform particularly well. So this is a situation where I would iterate over JKI. Now, I recommend maybe you pause the video and just look at this little code snippet to just assure yourself that this actually works as intended. But what's more interesting here is how we are doing the accesses now in this case. So you'll see that we actually have J as the first step. But what's interesting now is what's happening in this inner loop. You'll see that we are iterating I from 0 to N. And how does that actually affect our matrices? So we see here that we're accessing the matrix A. How are we actually accessing it? Well, K is relatively constant in the sense that it's been fixed at that point. Well, constant relative to the inner loop. Okay, obviously it's not constant, but while we're working in the inner loop, K is not changing, but I is. And when I changes, I end up moving from one row to another. Okay, so each time I increment, I move across to another row. And just as before, this now becomes a high risk operation because it's highly likely that I'm going to get a cache miss when I have very large matrices. Okay, now what happens in terms of matrix B? Well, in this case, we simply do a singular access. So in the very tightly nested inner loop, we're not changing it. We just extracted the value for BKJ once. And now we're sitting in a zero risk situation because I'm not iterating over it in the inner part of the loop. So it becomes a zero risk. But if I look at what's happening with C, so where I'm storing my answer, you'll see actually that once again, I'm iterating across the rows. Okay, so J is not changing, at least in the inner loop, but I is changing each time, which means I'm going to be moving down the rows again. Now, this tells me that I have a high risk of getting a cache miss. So if I compare the first one to this one, clearly this approach would be worse because in the case of IJK, so for IJK, we had a high risk, a zero risk, and a low risk. Okay. How did I write it out? Okay, well, the order is a little swapped around, but regardless, we had a high risk, zero risk, and low risk. But in the case of JKI, we're in a situation where I have a high risk, zero risk, and high risk. So in the one situation, I had one high and one low. Now I have two high risks, which means the odds of getting a cache miss become higher because of the way in which I'm iterating over the matrix. Now, it seems like such a simple thing, but it can actually radically affect how fast production level code is. And what's interesting actually, though the concept of matrix multiplication is so simple, all of machine learning, so for the AI field, machine learning currently with neural networks relies on matrix multiplication. The core engine is a huge amount of matrix multiplication. So making that efficient is actually very vital to things like convolutional neural networks and all of the fancy AI things you've been hearing about. All of it hinges on us efficiently performing such a simple type of operation. So in these two examples, you saw one that was kind of middle of the road and one that was poor, but we can actually leverage our new understanding to implement this approach more efficiently. So here we have another arrangement. So this is IKJ. So I'm going to iterate over I, then K, then J. And again, spend a bit of time to just sure out for yourself that this works, but we're going to focus on the manner in which we're moving across the matrices. So the first thing is what happens with A in terms of this inner loop. Okay, well, A is not changing because you see we're just using this R value and we extracted it just once. So in terms of the final inner loop, we have a zero risk operation because I'm not changing it. I'm just using the constant one in this inner loop over here. What's happening in terms of matrix B? Well, I'm iterating J from 0 to n. And what does J do in this case? Well, it's simply moving me across the columns. So I will be moving from one column to another column. But as I said before, the odds that these are next to each other in memory is very high. So we end up having a low risk operation. So what happens with the last matrix? So here we have a matrix C access. And again, we see that we're iterating over J, which means I'm going to be moving from column to next column and so on. And once again, we have a low risk. So the IKJ scheme has a wonderful zero risk, low risk, low risk. So it's clearly going to be our best choice if we have large matrices because we reduce the odds of getting a cached miss. And that can only be to our advantage because now we're not waiting around for data to get to the CPU to be processed. So it's a very simple idea, but it actually can be very, very powerful. Okay, so let's move on to something that's maybe somewhat more likely to be assembler specific. And actually, if you are interested in compilers, you'll see this type of technique used quite frequently. And it's the notion of common sub-expression elimination, okay, or simply CSE for short. Now, the idea is that the compiler will search for instances. Well, in this case, with assembler will be the compiler. We have to do the searching. But if we were in a higher level language, the compiler will search for instances of identical expressions. And by identical, we simply mean an expression that will evaluate to the same value. So there can be some subtleties in that definition. And then it does an analysis whether it's worthwhile replacing them with a single variable holding the computed value. So let's look at an example, because it's actually quite a simple concept to demonstrate, but it can be very useful depending on how computationally expensive the expression you are eliminating actually is. So here we have a little bit of algebra where I'm setting a to be b times c, and then I'm adding g. Okay, just say these are integers for simplicity. And then I want to calculate d, and d is simply b times c times e. Perfectly good looking bit of code. But the question is, can we do better? Well, if you think about it, we've done a bit of calculation here twice. So firstly, you will see that we've calculated b times c already. Okay? And now we're going to calculate it again over there. So I've calculated that product once, and then I'm going to calculate that product again. Now, obviously, it's still correct. It's going to give me the right answer. But the question is, did I need to calculate it twice? The answer is actually, I clearly didn't need to calculate it twice, because it didn't change between this line and this line. The value of b and c stayed constant. So we could actually rewrite this code as follows, where I'm going to store the product of b times c into temp, and then I'm going to do the calculation for a and d. So now I simply have temp plus g, which is basically this calculation over here, and then I'm going to go temp times e, doing this calculation over here. But now the big thing here is I've only done this multiplication to get temp once, which I did over here. I only had to do it once. Now there is a trade-off here. I have one less calculation, let's say one less calc, but I have one more variable. Okay, now oftentimes what will happen is this technique is particularly effective if you have spare registers. So the compiler sees that there's some registers that aren't being used, particularly ones that it doesn't need to maintain. It will use this trick. But the trick can also be used in a context where you don't just have spare registers, but then you need to kind of be more aware of, is it worth saving that one calculation at the cost of adding the one variable? Now this is kind of a borderline example because matrix multiplication is very simple. But can you imagine if this calculation over here was not just something simple like matrix multiplication? Imagine that was, not just normal multiplication. Imagine it was matrix multiplication like we were just discussing. Maybe I'm timesing matrix B by matrix C, and this matrix has 1,000,000 elements by 1,000,000 elements, and so does this matrix. Okay, so these are very, very big matrices. It would really be to my advantage to save the result of that calculation and use an extra variable, sure, but to avoid the necessity to recalculate it. So this is the general idea. Now, something I think that is also worth mentioning is that in this case, when we look at the code, it can kind of seem obvious that that expression and that expression are repeats of each other. But imagine you were in a situation where they were as follows. So I have A equals to B times C plus G, and then I have D, but it's a little bit different. It's actually B times E times C. Now, algebraically, they're the same, but you can see why it's a little bit harder for the compiler to realize it can perform common sum expression elimination, because it now needs to realize that this expression, this is multiplication, this is a terrible star, is equivalent to simply going B times C and then multiplying it by E, such that it actually has this duplication that it can eliminate. So it's quite a bit of algorithmics that go into play on a compiler level to actually maximize the sub-expression elimination in an efficient way. You could brute force this kind of thing, but it would obviously be a very slow compiler if it always brute forced. obviously in an assembler context, we're having to do this stuff kind of ourselves by looking at the problem at hand. But regardless, I feel it's worth mentioning that this is a little bit of an extra step that the compiler generally has to consider. Another common technique is what's referred to as strength reduction. Now, there are certain operations that are more or less expensive. So there may be, for example, an instruction that takes more clocks to compute than another instruction. Now, on modern architecture, most of your simple calculations take a similar amount of time, but on old architecture, there was quite a disparity between certain operations. For example, division used to be a very slow operation, whereas shifting used to be a very fast operation. On current hardware, they're relatively similar to each other. There's not such a big divide. But the premise of what I'll describe is still the same in a more broad context. So if, say, we know that using div is worse than using, say, shift right, I could utilize the following observation. Instead of dividing an integer by 8, so say I needed to divide it by 8, and it was always going to be 8. It was something to do with the algorithmics. I always needed to divide by 8. Instead of dividing by 8, I could actually shift right by 3 bits, which, as we know from when we did the bit shifting and bit manipulation section, is equivalent to dividing by 8, because it's for each shift we do to the right, it's divide by 2. So divide by 2, divide by 2, divide by 2. So in essence, we're basically saying divide by the 2 to the 3, and that's the same as dividing by 8. So if we knew that shifting was less computationally expensive than dividing, it would be to our advantage to rather use the shift. Now, that's maybe a very small difference between the two instructions, particularly on modern hardware. It's virtually non-observable, but on old hardware, it was a meaningful distinction. Another example, and this kind of goes against your typical coding practices that you will encounter, because we generally want to utilize functions and things like that to make our code look clear and succinct. But say I have a situation where I want to calculate x to the 3, okay? How do I go about doing that? Well, say I'm in C++ or C, I could use the function pow, okay? I could say pow x comma 3 would return x to the 3. Or I could simply go x times x times x. Now, it feels perhaps a little bit ugly to do the thing on the right, and particularly if, say, this was x to the 5, it looks very ugly. However, if you think about how one would have to implement the power operation, for simplicity here, let's just assume this is just power that only works with integer exponents. Obviously, there's a floating point variant, but let's just consider the integer version. How would we implement that? Well, there would be a loop that would be multiplying x against x, or like we have some kind of product that we're building up and we keep multiplying it by x, and we have some loop body that's doing counting and things like that. That's a lot of extra overhead compared to simply going x times x times x, which means that the right operation is likely going to be, or the one on the right is likely going to be considerably faster than the one on the left. Now again, I don't recommend in your normal everyday code that you start making the optimization where I convert this power to xxx, but if you're trying to eke out the extra performance, there is a place to actually gain the speed. The other thing is, if you're writing a compiler, it is to your advantage to realize when I can convert a complicated operation or an expensive operation to a cheap one. And ideally, if I can do that and a user doesn't even need to be aware that the compiler is doing it, that's great. That means I've succeeded I've achieved my goal as a compiler designer, because I've given you free performance, and obviously that's first prize. The other thing that's often done, and again, this is from the historical issue that division used to be computationally more expensive than multiplication, is that oftentimes instead of dividing something by x, so say I needed to compute x divided by y divided by x, on older hardware, again, it's less noticeable on new hardware, it was actually quicker to go y times 1 over x, where I got 1 over x using the reciprocal operation. So I would get the reciprocal efficiently. There's very quick circuitry to get a reciprocal. And then I'd multiply this by y using a fancier variant of Booth's. Oh, this is a floating point context. So using a fancier version of matrix multiplication than what the textbook covers. It's actually a field in of itself, efficient ways of doing these type of multiplications. But it's interesting that this was actually considerably faster than this. And actually this one is 2 operations and this one was 1 operation. So this was a reciprocal as well as a multiply. But on older architectures, it was faster than performing this division. Less so in modern architecture, particularly when we have dedicated floating point chips and we're not trying to emulate it, it's not as noticeable. And you can utilize these kind of tricks to a very extreme degree. You will not see them in most production level code, but if you start looking at low level code, for example, code in kernels and things like that, you will start seeing these tricks come up a lot because there's a big benefit to kind of being a little bit cheap in some sense with your coding practices, in that it almost looks like you know less but you're doing something more efficiently. For example, say I had to get x to the 5 going x times x times x times x times x. It looks like I don't know how to program perhaps, but in fact it's actually the faster way of doing it. You'll see here that there's an interesting little trick here, which is, for example, say I want to get a remainder after dividing by 1024. I could obviously use the division and then get out my quotient to remainder and extract it, or I could actually simply go x and use the AND operation against 1024 minus 1. Now you'll note here what ends up happening is I end up having a bit string of a bunch of 1s, which will give me a natural way of actually extracting the remainder. So it's quite a clever little trick. Now, something that I think is quite important to keep in mind is that sometimes the computational cost of an operation is architecture dependent. You'll have heard me multiple times on the slide itself say that on older architectures it was more of an issue, for example, to divide than it is on modern architecture. But this is generally a thing where different architectures have different strengths and weaknesses. For example, one of the big issues at this current point, well, it's not so much an issue, but disparity between, for example, AMD and Intel chips is that the AVX 512 instructions, so basically this is the bigger brother of those vectorized instructions we discussed, are much faster on Intel because they've designed circuitry specifically to make it faster. Now there's arguments as to whether that instruction set of AVX 512 is worthwhile using in general, but that's a debate for the CPU designers really. But what this tells me is that what is optimal on even Intel is not necessarily optimal on AMD, and it becomes more extreme if you have non-x86 architectures or even older generation architectures compared to modern architectures. But it's the nature of trying to optimize at this level, and that's why often it's informative for the compiler to know what CPU it's trying to optimize for. The next thing that we're going to discuss is this notion of using registers efficiently. Now, this concept of using registers efficiently was actually already mentioned when we started with the discussion of registers in general, but the premise is pretty straightforward in that we want to place commonly used values into registers. So say, for example, I'm looping over memory and I constantly access an element on my stack, or even something further away than that, say some heap-based memory. It would become much slower than if I just loaded that piece of data into a register and then just continually referred to that register. If I knew it was going to stay constant, it would be the faster thing to do. So generally speaking, when a value is frequently used, and quite often this is a situation where we have a loop going over a lot of calculation, it would be better to store that value in a register as opposed to continually re-accessing it from memory. Okay, so it's a simple enough thing to do. The next optimization to always consider is to use fewer branches. Okay, and a couple of the subsequent optimizations we'll discuss relate to this actually. And the problem with branches, and I did mention this when we discussed conditional moves actually, but the problem with branches is that they interrupt the instruction pipeline. Specifically, it means that the predictive pipelining might have to be undone. So the compiler, or sorry, the CPU is busy running your code, and there's two paths. There's path A and path B. Okay, so path A and path B. And it has to make a choice as to which instructions to load next, because it wants to be ahead of the current execution. So it says, I'm going to guess that I'm going to load from A. Okay, so I've loaded from A. But now I get to the actual decisive moment where I can actually make the decision as to which way to branch, and unfortunately, say the CPU made the wrong choice. It means I will now have to go down path B, and I'll have to unload all of what I've loaded in. So I have to undo the predictive pipelining. Now the compiler will actually frequently reorder blocks of code to reduce branching, and it does this quite intelligently. But again, in an assembler context, we have to do this ourselves, but it's good to understand why it's trying to do it, because it's actually avoiding this failed pipeline prediction has a very big effect on the actual speed of execution. And obviously this is where conditional moves can help a lot in an assembler context. I mean, it's in a high level context, you don't really have a conditional move type operation. You can hint to the compiler to do it with how you write your code, but it's not always clear that the compiler is going to listen to what you want it to do. Now in this vein of having less loops, it's why we actually converted our loops to branch at the bottom. If you recall from when we discussed looping, where this idea that instead of having a while loop, it was actually better to have an if statement wrapped in a do while. So in essence, or the shorthand way of saying this is we want to convert our loops to branch at the bottom. So say I had this for loop over here, I would simply convert it such that I have an if statement at the start, and then I have a do while. And by doing this, I end up having obviously a reduced number of instructions within the loop. So that's nice in the sense that the whole body can maybe fit into the instruction cache more easily. But more importantly, generally speaking, is that we have far fewer branches. So that's obviously ideal, because in terms of the continually executed part of the code, we'll have less jumps. So there's less places the CPU can make the incorrect prediction. Now I should just stress again is that though this approach is faster, you should not do it when you write C or C++ code, because your compiler can handle that for you. Simply turn on O1 optimization and it will do this automatically for you. Again, try and disassemble a bit of code and you'll see it actually happening. But again, it's good to know why it's happening and why that choice was made. Also, if you write your own compiler and you need to try and induce some optimization, it's good to know that you should employ this technique. But I would advise against warping your C++ code to look like this if the compiler can do it for you. The next concept, or the next trick, is to unroll loops. Now again, this is a bit of a funny one in that when you started learning how to program, you would see sometimes people would try and have the instruction repeated many times instead of having a loop. So say they had to do something 8 times, they would repeat the same instruction almost 8 times instead of having a loop, which would have maybe been a little bit clearer. And in worse examples, maybe you needed to repeat the instruction 50 times and you did it directly instead of having a loop. Now, as you learn to program more, obviously you realize, no, wait, this is a bad idea. This code is very hard to maintain and it's maybe easy to have a bug. Let me rather have more coherent code and just write a loop. It's also quicker for me to write. And that's how you would normally go about it. Now, unrolling loops is in some sense the opposite of that, in that in some situations it is faster for your program execution if you do not actually have everything in a loop. If you can completely flatten the loop, so say in that example, say we knew that there would be 20 loops every time, it would be to our advantage actually to not have the loop at all and repeat the instructions. Now, again, I don't mean that you should write your code like that, but you can tell GCC that you actually want to unroll all your loops using the following command, and this will induce a bit of a trade-off. What will happen here is that your executable will become larger. So say you, for example, had a loop that you knew would be executing 1,000 times and you perform this unroll. That's a lot more instructions if it's repeated again and again and again. So your actual text segment of your program can become considerably larger. But there's a trade-off happening there. There's less jumping, which means the program will execute faster. However, the program is now larger. So it's not a perfect win-win, but generally speaking, it's a trade-off that is useful enough to make that it's done quite frequently. There's a couple of other benefits for this, is that the first thing is you can do this to try Okay, this way. It frees up your CPU to do out of order execution, particularly if you make each unrolling use different registers to reduce instruction dependence. Now, there's two things actually going on here, and I'll kind of elaborate a little bit more on both as we go on. But the first thing here is that if we have less instruction dependence, it's easier to figure out when I can perform my common sub-expression elimination, because I know that one instruction is not affecting another. So it makes it much easier to do that kind of calculation, or that decision making process, and also frees up the CPU to do what's called out of order execution. Okay, I'll come back to that term shortly. The other thing is it can actually do more pipelining, because there's no jump coming up, so it can load a large amount of instructions with high certainty that they'll be executed, and this actually can allow for more parallel execution. And again, this is something that you may not be aware of, but in some situations, say you have 3 instructions, the CPU can technically execute all 3 at the same time in some situations, because the order in which they executed didn't matter. Now, this notion of parallelism is really a very hardware level of parallelism, so I don't want you to fall too far down that rabbit hole, but it is an upside of this unrolling. Let's look at an example. That's something that's a little bit more quantifiable, where we could see this type of effect. Let's say I have a function called addArray, and all it does is it loops through my array and it just returns the sum of all the elements. Okay, so straightforward program. You'll see here that each element is a long, we return a long, and I just pass through the size of the array as a long as well. So first thing I'm going to do is I'm going to set RAX to be 0, so this is basically going to be my sum. I'm going to add the first element of my array to RAX. I'm going to increment RDI by 8, and again I'm incrementing it by 8 because remember, a long is 8 bytes, or said otherwise it's a data quad word. Then I'm going to decrement RSI. Remember, RSI contained my size. Then if RSI has not hit 0 yet, it means that the result will still be positive, so I'm going to then jump if greater, so basically if it's greater than 0, back up to this add words, and I'm going to repeat again and again until we end up in a situation where RSI became 0. Then this greater than will not trigger, and we return the answer, and it's already an RAX for us. So simple enough code, but we can try and utilize this unrolling technique. But generally this unrolling technique comes with a couple of caveats. So for simplicity here, let's consider a multiple of, or the array size being a multiple of 4. Now what would actually happen in practice here, before I go into the detail, is that the compiler may actually generate multiple versions of the same function with different types of unrolling. Again, there's a trade-off. This actually induces quite a much larger text segment again, but there's a fair amount of benefit to be gained by performing the unrolling. So we'll see here that I now am going to have 4 registers being used as my partial sums. So before I had one sum really that I was just adding to the whole time. Now I'm going to use RAX, R8, RCX, and RDX as partial sums. So I'm going to keep all of them, start them at 0, and then I'm going to add elements to them as I go. Then I have my loop body, but it's now changed a little bit. I'm going to add the first element of my array to RAX, the second element to R8, third element to RCX, fourth element to RDX. Okay, so basically in a situation where this one will get added to RAX, this one will get added to R8, this one will get added to RCX, and the last one will get, or the fourth one rather, will get added to RDX. Then I'm going to add 32 to RDI. Now the question is, why would I add 32? Well, I've actually accessed 4 elements already. So if I want to get to this element over here, next time I loop around, I would have to add from this original pointer 32. Then I'm going to subtract 4 from RSI because I've processed 4 elements. Then I'm going to use the same logic as I did in the previous example, where I'm going to jump back up to add words if the result of the subtraction yielded a positive number, so if it was greater than 0, and I repeat this process again and again. Once I've gotten to the point where I actually end up with RSI being 0, I'll no longer jump, And all I now need to do is I need to kind of gather up all my partial sums. So now I'm going to add RDX to RCX, add R8 to RAX, and then lastly, I'm going to simply add RCX with RAX. And then I'm going to return the result. Now this feels like it could be worse because it's a much larger piece of code. I even have a little bit of extra instructions at the start and the end. But the big computational chunk in this code is this loop. Imagine I had an array of 1 million elements again. This loop is what's going to be doing the heavy lifting. So what's this little bit of constant time computation at the start and the end is almost irrelevant. But if I can reduce the amount of branching in this, it's greatly to my advantage. And because I actually utilized different registers for the partial sums, it doesn't matter in which order I executed this one, this one, this one, this one, or this one. Oh, sorry, of these four. It didn't matter in which order I did the execution. This means that the compiler could actually, the CPU could technically execute this in the order 3, 2, 4, 1 if it wanted to. Now, the CPUs in modern CPUs do this out of order execution quite frequently, and it's a little bit uncomfortable for us because when you write code, you think the CPU will perform it exactly as you intended in the exact order that you stated it, particularly if we're writing it in an assembler level. However, the CPU, in order to actually make them run faster, they will perform this out of order execution only when the result is equivalent. So it doesn't change the outcome, so it has to do a little bit of intelligent thinking on that side. But it means that if we write our code to facilitate it, we give the CPU more tools to make this possible. Now, there's a couple of reasons this could happen. It is possible that for some reason, it might realize that it's more likely to get a cache hit on these two if it did these two calculations first. There's a whole bunch of heuristics and very complicated CPU design that goes into making out-of-order execution effective. But out-of-order execution is an interesting kind of concern in some sense with the CPUs because it has been used to kind of demonstrate some or exploit certain CPU level bugs. So that's something to keep in mind. We seem to have not gotten too many, but I'd say in the last 5 or 6 years, Intel has been hit by many of these bugs that are related to out-of-order execution, and that out-of-order execution became an issue when the out-of-order execution resulted in a result that was equivalent, but it made a higher privilege system call than it was meant to, even though the result wasn't used, and then it was actually able to utilize a side channel to figure out what was going on. Sorry, that's a slightly more complicated detour, but there's pros and cons to out-of-order execution, though it's a common technique, a very common technique in CPU design, though Intel pushed a bit harder on that side than AMD has. The next technique is this idea of merging loops. If you have two loops that have the same limits, it may be actually worth considering merging the loop bodies. In this way, we'll end up having less loop overhead. So let's consider this example over here where we have these two simple loops. And the first loop is basically just storing the sum of BI and CI. And the second loop is simply storing the difference of BJ and CJ. Now, in principle, nothing would prevent us from actually having one loop and having both of these instructions in it. Now, in this example, it would be a perfectly reasonable thing to do because it reduces the overhead of having a whole other loop. So after merging, we have the slightly more concise code, and we've simply removed unnecessary loop overhead. Now, on the other end of the coin, sometimes it makes sense to actually separate loops. So if a loop is running over two disjoint pieces of data, so data that's perhaps very far apart from each other in memory, it might be profitable to actually split the loops. That's because if I have an instruction that is accessing memory in one location and then another instruction and that location is far away, and this is all in a loop, each time I go from this location to this location, it's possible that by experiencing a cache miss and loading in a bunch of data, I end up getting another cache miss because I've kicked out this data. So in a situation where you're working on two disjoint pieces of the data, it may actually be profitable to split the loop. So in this situation, it would be a case where the potential cache utilization can add a greater speed increase than the extra overhead incurred by having two loops. Now, unfortunately, with this one, it's quite hard to know up front. There are some exceptions, but generally it's not that easy to know that immediately. But your best bet is that real-world testing is often the best way to determine if the split is worth it. So you kind of need to benchmark and see if the speed after or before the split is actually substantial. The next type of optimization that one should always consider doing is to move loop invariant code outside the loop. So in this example, we're calculating a power of 4.5 to the power of 2.5. Now in this situation, it's a fractional power, so it's actually going to be a relatively computationally heavy calculation for what it is at least. But in this example, we see that we multiply the element by the same value, the element of the array by the same value each time. So if we were to execute this code as it stands here, we would calculate that power n times. But there is no need to calculate the power n times. It would rather be more effective to simply calculate that power once outside the loop body and utilize that value within the loop body to prevent this unnecessary recalculation of the same value. The next thing that's quite useful to do is to remove recursion. Now, obviously, each time I make a function call, I end up incurring extra costs because I have to build a stack frame. I'm moving to another function, so it's another branch in essence. Then I have to come back. There's a lot of extra things that have to happen with recursion, in addition to, for example, ensuring that you actually reset the registers that you're using such that everything is still compliant with the system ABI. But generally speaking, eliminating tail recursion specifically is a very effective way of gaining speed. Now, actually, a lot of compilers will unwrap your recursion into iterative versions if they can detect they are in fact tail recursive. Sometimes it's not that clear for the compiler to do it, but generally speaking, the compiler is able to convert a fair amount of your tail recursion code to be iterative if you set the appropriate optimization flags. However, this notion of removing recursion is not always appropriate in the sense, if you're just aiming for a speed bump at least, in that if you have to simulate a stack like recursion naturally gives you because you have the stack frame, recursion will itself probably be faster because you don't have to maintain the separate extra data structure. Obviously, if you don't have enough stack space for the size of the stack, then obviously doing it iteratively with a stack is the better bet. But moving that way is not done for a performance speed gain, at least. But if you have tail recursion, removing recursion is definitely the faster approach. The next thing is to eliminate stack frames. Now, remember when we described how to set up and destroy stack frames, the one thing we still have to ensure, obviously, is that we maintain that 16-byte alignment, but we don't need to actually build that linked list type structure. That linked list type structure is important for general coding and for debugging, because obviously we need to be able to iterate through the functions. We have to move back up the function levels, but we are actually able to remove those stack frames and remove an extra instruction from each function. So if you're really pushing for performance, you can do that. And this is generally actually what is done if you're saying an IDE or something, you set it to be in release mode. You can also manually specify this using the following commands where it will omit the frame pointers. Leaf functions themselves don't actually need to even worry about stack alignment unless they're using an operation itself that depends on the stack alignment. So there you can naturally get rid of the whole stack frame without really worrying. The next thing is to inline functions. So again, this is the type of thing that would make your own code look very ugly. So instead of calling a function to do some computation, you simply paste in essence the code that would be the insides of that function. And each place that function call would occur, you do the same thing. Now, obviously that's terrible from like a fundamental programming principles perspective, because it makes your code very, very hard to debug. I mean, if you want to change how that function works, you have to change it everywhere. It also increases the text segment size drastically, but it can actually make your code considerably faster. But again, this is the kind of thing that your compiler can do for you rather in a relatively painless fashion with the appropriate optimization flags. So I wouldn't recommend that you naturally inline your code, but let's say we're not in a situation where we have a compiler. How do we go about this? Well, you could just paste the functions directly, but assembler is hard enough to read as is. So it's going to make your code very hard to read, so a lot less readable. But if you're in the position where you're trying to really maximize your assembler code, I would recommend that you explore using macros. So Yasm, as well as its variants such as Nasm and the likes, have a macro functionality that in essence will just paste the code for you, but it just helps a lot from a readability and a maintainability perspective. But inlining a function is in fact faster, but again, it's that trade-off. The text segment becomes larger, but you have less branching. So that's pretty much the trade-off that is happening. The other concept, and we actually really discussed this when we partially unwrapped that loop, is to reduce dependencies between instructions to allow for superscalar execution. Now, the idea is that we want to use different registers to try and reduce dependency. And by dependency, I mean that the order in which a set of instructions would be executed is invariant or irrelevant rather, such that no matter what order I executed that set of instructions, I would get the same answer. And this is good or important to do because the CPU actually has multiple computational units in a single core. So it can actually oftentimes perform 2 additions on the single core in the same computational unit. Again, this is very hardware level parallelism. It's somewhat different to threading and things like that. But by allowing or writing your code such that you have reduced dependencies, you can benefit from the superscalar execution, and you can also benefit from out of order execution in that the order in which those instructions are executed do not matter. We also get more out of our pipelining, because the more code that is independent of what happened before it, the less harsh a potential pipelining dump will actually be, because there will be instructions that do not actually depend on which branch was taken. And you can keep more computational units busy, which is obviously good if we're trying to maximize performance. And as you see in this example before, the order of execution here between these 4 instructions does not matter, which means superscalar execution is in fact possible, that as many computational units as it has in a single core could actually execute in parallel. And even if we don't consider the parallel nature, the order that it's executed for out of order execution is obviously up to the CPU, which means there's the potential to eke out a lot more performance here. The next general trick I would give you is that you should utilize specialized instructions. Now, the x86 architecture has a very vast array of instructions, many of which are basically carried over from earlier versions of the architecture, because obviously, as I mentioned at the start of this course, I mean, we had 16-bit assembler, which got, or 16-bit x86 assembler, which got extended to the 32-bit, which then got extended to the 64-bit, so there's a lot of baggage. However, as the architecture has evolved, oftentimes they would introduce new instructions, and you could oftentimes capitalize on these new instructions to eke out a lot of performance. And generally speaking, it would take longer for the compiler developers to change their compilers to maximize those instructions than you as a programmer could actually just incorporate that into your code. Some other things to keep in mind with these specialized instructions is that we discussed simmed floating point instructions. That's how we did all our floating point calculations actually. But there are actually simmed integer instructions, so you can also do packed integer calculation. So that's something to keep in mind if you're trying to maximize performance. And obviously there is this idea of using the AVX instructions instead of the normal SSE instruction, so that's basically the YMM registers, as well as actually utilizing the ZMM registers if you actually have AVX 512 instructions available on your CPU. These are somewhat more recent on most CPUs. Your Xeon CPUs have had them for a while, but not so many of your desktop CPUs. Now, to kind of give you an illustration of something where you could utilize a specialized instruction to gain a nice performance boost, and this is something a compiler would not in fact do, or at least not the compilers I've encountered. Remember the question, or it was a slightly different phrasing of this question, but we assume we have 2 variables in our data segment, A and B, and say they're both quad words, and you had to complete some ASM to calculate the hammering distance between A and B and store the result in the RX register using instructions that you knew, and you kind of had a fixed layout. Now, if we actually have a very vast understanding of the instruction set, we can utilize that knowledge to actually write this hammering distance calculation very quickly. Specifically, we only need these 3 lines. So what am I doing here? Well, first thing is I'm going to load A into RAX, then I'm going to XOR B with RAX. So what will this give me? Well, basically this will give me a bit string where I'll have a 1 if A and B at that location were different, and a 0 if they were the same. Okay, so I end up having the string. And now remember, the hammering distance is the number of bits that are different. So actually all I want is the sum of elements here. So the sum of all of these elements, so the 1 plus 0 plus 1 all the way through, would actually end up giving me the hammering distance. So it would be the number of bits that were different. So how do I do that? Well, we could use a loop like we have done before, or I can simply use this pop count instruction. And actually what that does is it counts the number of ones in this register and stores the result in this destination register. Now Rx will contain the number of ones, and in this case the number of ones is in fact the hammering distance. Now here the knowledge that pop count existed meant that we didn't even need to use a loop. So this may be a kind of specific example, but you will find a lot of encryption relies on these kind of tricks where we have long strings of XOR operations, and actually you will see that if you look at the x86 instruction set, there is actually ways you can do block level SHA type encryption on individual blocks, because they can do it so fast at an instruction level, much faster than if you coded it. Even in assembler, if you have the direct instruction, it means it's likely there's hardwired ability in the CPU to actually do that calculation for you. So utilizing specialized instructions is definitely to your advantage if you're trying to maximize performance. And that brings us to the end of this lecture, as well as the end of the assembler content for this module. So I think with this section, I think your best bet in terms of studying it is just to kind of think of if I gave you, for example, a function, what would be necessary to actually make it a faster function using these tricks, or if I gave you a start point and an end point, like a function before optimization and a function after optimization, to maybe identify what techniques I used to actually perform that optimization. Was I, for example, maximizing my ability to encounter superscalar execution? Was I unrolling? Things like that. Other than that, that brings us to the end of the assembler part of this course.